Hello everybody and welcome to the 19th lecture of MHM 42780. In our previous lecture we talked about heat exchanger analysis and we talked a little bit about LMTD method. We didn't solve an example, but today we are going to do it. Before starting it, just a little bit of a reminder of what we discussed during the last lecture. We said that LMTD method is very effective when we have the inlet and outlet temperatures of hot and cold fluids, and when the mass flow rates are known. We also said that there is another situation that we might face when we are going to design a heat exchanger, and it's the time that we don't have the inlet and outlet temperatures. We also said that there is another method to deal with those kind of heat exchangers, or the same, the result should be the same, but there are different methods. So basically, based on the information that we have at the beginning, we can use either LMTD method or epsilon NTU method. Okay, but we are going to speak about epsilon NTU today. Before that, we are going to solve an example. Okay, so when I said that the inlet and outlet temperatures of hot and cold fluids should be specified, it doesn't mean that we are going to mention all of them during the examination or like a final exam, for example. There are many ways that you can find the unknown inlet or outlet temperatures by using energy balance. So for example, if I give you the inlet temperature of hot fluid, inlet and outlet temperature of cold fluid, it should be very easy for you to find the outlet temperature of hot fluid. Okay, you find all those temperatures by using energy balance or any other method, and after that, when you have all the temperatures, is the time that you know that you can use LMTD method. You calculate the log mean temperature difference. If it's necessary, you find the correction factor for it, and after that, when you have a correction factor, when you have the log mean temperature difference, it's very easy. We talked about it, that Q dot basically is equal to U, which is overall heat transfer coefficient, AS heat transfer surface area, F correction factor, and delta T log mean temperature difference. But we also, if you remember, we said that it's like a CF. What does it mean? Counterflow. Okay, so now by just like all those information that we talked during our last lecture, we are going to solve one example together. And after that, when we are done with this example, we are going to speak about effectiveness NTU or epsilon NTU method. This this question that we are going to solve together is question 11.73 of your textbook. It's saying that a single pass cross flow heat exchanger with both fluids unmixed. Okay, many information here. We are just going to write it down. Single pass cross flow both fluids unmixed. Has water entering. Water is entering from that side 16 and exiting at 33. So the water is all or cold fluid. Why? Because comes with the lower temperature and goes out with a higher temperature. While our hot fluid is oil, which comes in with 38 degrees and goes out with 29 degrees. Okay, so that's another thing that we know. The properties of oil is given. Something is also is given 0.9 cubic meter per minute is not mass flow rate, but there are some ways to find it. And the area of heat exchanger is given as well. What is asking is the value of overall heat transfer coefficient. So for brainstorming, immediately we say that okay, overall heat transfer coefficient, we can say that easily the Q dot is equal to UAS if it's necessary correction factor delta T LM CF cross flow, and after that U easily will be AS F delta TLM divided Q dot on top. So here AS we have it 20 square meter. Correction factor, we don't know if we have to have it, we need to look into it. And log mean temperature difference for cross flow, but just think about that. Okay, first we need to see if we have all the temperatures. Yes, all the temperatures are given so easy, even we don't have to do anything about it, very simple. So this is very easy to find. This Q dot, we need to find this one as well. And when we have this Q dot log mean temperature difference and F that we don't know, we need to look into it, we can find the overall heat transfer coefficient. So here let me just write down all the information that we have here. So oil, we know that is our hot fluid. Okay, so the T hot in, we said that is 38. T hot outlet, we said is 29. We also said that we have some information regarding the property of hot fluid or oil. So Cp hot fluid is 1.93 kilojoule kilogram Kelvin, and rho H is also 870 kilogram square meter. So we have all this information. The other stories is like normally we are interested in mass flow rate, but mass flow rate, we know that, for example, m dot h, the unit needs to be kilogram per second. But what we have here is like cubic meter per minute. Okay, so let's see how can I do like a cubic meter per minute if I can divide it to kilogram per second. So I say that okay, m3 minute multiplied by minute per second. Okay, so now I have a cubic meter per second, and if I multiply that by kilogram per cubic meter, what I'm going to have is kilogram per second. So I just like created the same unit as m dot, which is the mass flow rate of oil. So m dot h will be 0.19 minute multiply by 1 divided by 60, because 1 minute is equal to 60 seconds, multiply by, what is this? It looks very familiar, is density. So we just put the density here. So the mass flow rate of hot fluid or oil will be 2.6 755 kilogram per second. You see, it was so easy, but that's the reason why always I tell you that you need to write the units, because will help you a lot to understand what information you have and how you are going to transfer those information. Okay, now let's go back to the question, and let's see if we really need to find the correction factor. When correction factor was not necessary, we said that if we are having like a double tube heat exchanger, we really don't need to to calculate any correction factor. So it's like a single pass, like a double pipe heat exchanger. But in this case, we see that it's not the same. If we go back to the figure 11.19 of your textbook, and you go to the section C, you see that the section C is say that, for example, for single pass, cross flow, both fluid unmixed. Let's go back to the question and see if it's exactly the same. Single pass, cross flow, both fluids unmixed. So it's exactly the same. So this is the one that we need to deal with. Okay, we just like, so we need to find the correction factor, but now it's how to calculate it. Okay, it's very simple. First we need to find P. Secondly, we need to find R, and after that, by having these two values, we can go back to figure 11.19 section C and find the correction factor. Let's do it. Okay, so P, we said that basically is equal to the outlet temperature of cold fluid, inlet temperature of cold fluid, inlet temperature of hot fluid, inlet temperature of cold fluid. Okay, so we just like write them down because we know the numbers. So it's 33 degrees minus 16 degrees divided by 38 degrees minus 16 degrees. So it will be equal to 0.77. We also need to find R. So R is equal to basically the inlet temperature of hot fluid minus outlet temperature of hot fluid divided by outlet temperature of cold fluid minus the inlet temperature of cold fluid. So we just like put the numbers because we have all those temperatures. So 38 degrees minus 29 degrees divided by 33 degrees minus 16 degrees, which gives us 0.53. Now if we go back to the if we go back to the figure and section C, we see that okay, we don't have 0.77, we don't have 0.53. So what we are supposed to do, we need just to find it. For example, I say that I'm assuming 0.77 is here. I can use the ruler as well, but I think that's a good assumption. I just like put go a line from here up the way up. So what is this line? This line is P is equal to 0.77. Okay, but we have the same problem with R as well. We have 0.2, 0.4, 0.6, 0.8, but we don't have 0.53. For 0.53, I can assume that it's somewhere here between 0.4 and 0.6, but closer to 0.6. So if it's like this, I'm just like going to use the same kind of trend. Closer to 0.6 than 0.4. I think that's a very good estimation. So here we can say that okay, what is this? This is the line of R is equal 0.53. This point here is our correction factor, which is 0.85. Okay, so correction factor is 0.85. But if we want to be more accurate, so we can use the ruler, no problem. But if it's like if you write 0.84, is still okay. Or if you say that okay, I calculated the correction factor 0.86 is still fine, no problem. So now we have the correction factor. Let's go here. We have the correction factor. Now we need to find the delta T Lm, or log mean temperature difference, but for cross flow. Okay, first we are going to write down the correlation. The correlation is the same, the correlation doesn't change if we are talking for parallel flow or counter flow, but the only thing that will change is how we calculate delta T1 and delta T2. Because we are speaking about a counterflow, so we said that okay, let's say here is counterflow. Always if you do this one, it's very easy for you to understand. For example, now we are speaking about counterflow. So this is hot inlet, hot outlet, cold inlet, cold outlet. So this is delta T1 and this is delta T2. So delta T1 basically is equal to inlet temperature of hot fluid minus outlet temperature of cold fluid, while delta T2 is equal to outlet temperature of hot fluid minus inlet temperature of cold fluid. Is for counterflow. But for parallel flow, if we do exactly the same thing, very simple. Thi, Tci, Tho, Tco. This is delta T1 and this is delta T2. For parallel flow, delta T1 is equal to inlet temperature of hot fluid minus inlet temperature of cold fluid, and delta T2 will be equal to outlet temperature of hot fluid minus outlet temperature of cold fluid. Okay, so we know that it's like a counterflow, so this is the one that we are going to deal with. Just like put it here. So delta T1, inlet temperature of hot fluid 38, outlet temperature of cold fluid 33 is 5, and delta T2 is equal to outlet temperature of hot fluid 29 minus inlet temperature of cold fluid 16, so it's equal to 13. Delta T log mean temperature difference when we are talking about counter flow will be equal to 5 minus 13 divided by 5, 13. If we calculate, this is equal to 0.955, some numbers after that, and this is minus 8, so what we have, the final will be 8.372. okay, we have a correction factor. We also have the log mean temperature difference for counterflow, which is 8.372 centigrade. Okay, Now if we go back to our brainstorming here, we see that okay, now what we have here, we have this one, we calculated the correction factor because we realized that it's not just double pipe, so the correction factor is needed. We also calculated the log mean temperature difference for counterflow. The only thing that we need to find is Q dot here. Okay, now let's go and calculate the Q dot, and after that we will be fine. How I'm going to find or calculate the Q dot? It's very simple. We said that there is a energy balance in heat exchangers, and we said that we are going to neglect those energy losses. So all the heat or energy that it's going out of the hot fluid is going to be absorbed by cold fluid. So if we can find the amount of absorbed energy by cold fluid or amount of energy that is going out of the hot fluid, we are going to be fine. So basically, cold, if you remember, we said that if it's C, CPC, TC outlet minus TC inlet. We also said that Q dot H is M dot H, CP H, T inlet hot, outlet hot fluid. And we said that this needs to be equal because of the energy balance. So now let's go back and see what information we have here. So if we go back to the question, we can see that okay, we don't have any information regarding the M dot of cold fluid, which is water, but we managed to find the mass flow rate of hot water, which is oil. Okay, we also have the heat capacity of hot fluid. So it looks like that all the information is there. M dot H we have it, CPH we have it, the inlet temperature of hot fluid we have it, outlet temperature of hot fluid we have it. So it's very easy for us to find the Q dot. So Q dot, it will be equal to M dot H, or hot mass flow rate of hot fluid. We calculated 2.755 kilogram per second multiplied by CPH, which we said that 1.93 kilojoule kilogram Kelvin. We also said that it's 13.8 degrees. It's like we have both of those temperatures. So but keep in mind that when here is kilojoule, our final unit will be kilowatt. Otherwise you need to transfer this one or multiply it by 1000, and after that make it joule if you want at the end the unit be watt. So basically it will be 4.785 multiplied by 10 to the power of 4 watt, or 47.85 kilowatt. It's just either you use this one or you use 1930 joule kilogram Kelvin. Okay, that's the reason why I always tell you to write the units, because sometimes it's like if you don't give enough attention, you just like make a small mistakes, and after that all the calculation from that point will be wrong. Okay, now we have all of that, so let's go and find the U. We said that our overall heat transfer coefficient is Q dot ASF log mean CF. We have all of them, so it will be 4.785 10 to the power of 4 watt 20 0.85 8372 Kelvin or centigrade, sorry, and the final will be 336 watt to C. This is the U. Okay, so as you see, it was very easy, but we had to do a little bit of brainstorming at the beginning to know where to start, and after that we took all those steps one by one together. Now we are going to talk about effectiveness or epsilon NTU. I told you in our last lecture that when the fluid inlet temperatures are known and the outlet temperature are specified or can be determined from the energy balance, we can easily use log mean temperature difference. Exactly the previous example that we solved together. But if just inlet temperatures are known, so both of the outlet temperatures, so you don't have the outlet temperature of cold fluid, you also don't have the outlet temperature of hot fluid, so it's very difficult or almost or impossible to find those two temperatures by using just like simply the energy balance between hot fluid and cold fluid. So basically it means that you cannot use the LMTD method. There is another method that we are going to talk today about it, and we call it effectiveness NTU or epsilon NTU method. NTU, what is it? Is number of the thermal units. Effectiveness epsilon, so basically that's it. This method was first suggested by Case and London in 1955, and basically this method is based on some dimensionless parameters, especially called heat transfer effectiveness epsilon. To define the effectiveness of heat exchanger, as you can see here, first we need to determine the maximum possible heat transfer. So as you can see here, the epsilon or effectiveness, heat transfer effectiveness, is Q dot divided by Q max, and does make sense because we want to know that what is the maximum heat possible heat transfer rate, because if we don't have the maximum possible heat transfer rate, we can't really find the effectiveness. Okay, but the problem is, or not problem, like a challenge is, when we are getting the maximum possible heat transfer rate, in what kind of situation you are going to get the maximum heat transfer rate. This like Qmax or maximum heat transfer rate could in principle be achieved in a counterflow heat exchanger. Okay, but is there the only criteria is to be the counterflow? No, it's like a counterflow as well as infinite length. Why? Because you are giving the both fluid enough time to transfer all the energy, so to get to achieve the maximum possible heat transfer rate. So let me just write it down here. The maximum Q dot max will achieve when the heat exchanger is counterflow and when the length of heat exchanger goes to infinity. In such a heat exchanger, one of the fluids would experience the maximum possible temperature difference. So basically what we are going to do is that in the counterflow there are going to be very close to each other. So THI, THO, TC inlet and TC outlet. So to understand better, consider a situation where here, for example, the maximum heat exchanger, temperature difference. The maximum the temperature difference is between these two. Why? Because let's say we have we just have 4 different temperatures, nothing more than that. We know that T or inlet temperature of hot fluid is very close to the outlet temperature of cold fluid because we are talking about the counterflow. So the maximum heat transfer will happen when the delta T is TH inlet temperature of cold fluid, hot fluid minus inlet temperature of cold fluid. Okay, so when this is our temperature difference, we are going to get the maximum possible heat transfer rate. But to understand the situation a little bit better, let's just make an assumption. Okay, if you remember, we called something like capital C, and we said that it's a heat capacity rate, and we said that okay, capital C is equal to m dot Cp. Okay, if we define the heat capacity rate for both hot fluid and cold fluid, we will have something like that. Cp, C, and heat capacity rate of hot fluid is m dot H Cp H. So just assume that we have this situation, the situation that heat capacity rate of hot fluid is much bigger than the heat capacity rate of cold fluid. So what will happen? We also said that from the energy balance, we also said that Q dot C is equal to Q dot H. We also know that Q dot C is C delta T, C if I just put it like that, and Q dot H is equal to CH delta TH. So when the heat capacity of hot fluid is greater than the heat capacity of cold fluid, in order to satisfy the energy balance, we need to have this one. It's very simple. Am I right? Why? Because if it's not, we are saying here that the heat capacity rate of hot fluid is higher than the heat capacity rate of cold fluid. So in order to achieve this equilibrium, we need to have a higher temperature difference in a cold fluid to be able to achieve it. So the cold fluid would experience the larger temperature change. The larger temperature change, it is something that we were looking for maximum possible heat transfer rate. So that's Q dot max here is equal to Q dot C. Okay, but you might say that okay, q dot c, so basically then it is c minimum. Why the heat capacity rate of minimum? Because we talked about it here. When the heat capacity rate is lower, then the temperature difference is higher. So q dot max will be the C mean and Thi minus Tci. Okay. How we are going to find the C minimum? Basically, we calculate the heat capacity rate of cold fluid and hot fluid. Which one is lower will be our C min. In this specific case, we started with assumption that the heat capacity rate of cold fluid is lower, so basically it will be equal to Cc. Okay, so that's basically it. It's not a very complicated method, but let's here we just like showed the different options. So first we said that it is exactly the same if the C minimum is the heat capacity rate of cold fluid. This is epsilon, how it's going to be calculated, because the maximum will be the C minimum multiplied to the maximum heat transfer maximum temperature difference that we said in a counterflow. It happens in a counterflow configuration, and it's always H or inlet temperature of hot fluid minus inlet temperature of cold fluid, because always they have the biggest temperature difference. And q dot on top, so of course is a cold, so Tc out minus Tc in. But what if the heat capacity rate of hot fluid is the minimum one? So of course the q dot max, the temperature will stay the same. The only thing that happens is here we need to put the heat capacity of minimum, but in this case, because the Ch is lower, so the Ch will be C minimum, but on top it's the business is as usual, Cs delta T H, and it's delta T C. Okay, so I think it was very simple, but let's try to find the epsilon, because we did all those stories to find the epsilon. Th out, Th in, C's, for example, here we are saying that inlet temperature of the hot fluid, inlet temperature of cold fluid, so fine. We said that in the majority of the time we have these two, but we don't have this, the outlet temperature of cold fluid in this case. In the other case is the same. We don't have this. Here is wrong. It is inlet. We don't have this one. We have all those three inlet, but we don't have the outlet temperature of hot. So when we don't have these two, how we are going to find the epsilon? Let's try to see if we can find it or calculate it. If you remember from LMTD method, we had something like that. It's from LMTD method for parallel fluid. So we said that T outlet temperature of hot minus outlet temperature of cold minus TCI is equal to minus UAS m dot h CPH plus 1 m dot c CPC. It was for a parallel flow heat exchanger. If you I don't know if we need to talk about it or just like solve it one more time. Let me see how much time we have. If I can just like, yeah, I can just like talk about it. We can continue next week with the rest, but let's see how we get to this equation from LMTD method but for parallel flow. So now what we are going to do, we are going to find this one to get to that point. Okay, sorry. So you remember last lecture we talked about some assumptions. Okay, if we apply all those assumptions, we say that for some kind of like a differential energy balance. So instead of like talking about temperature difference, when we are talking about a very small temperature difference, we are speaking about the differential energy balance. So basically Q dot C, it's from LMTD method. It was like this dt, and differential H was m dot H CPH delta TH. So very small change in the temperature of a cold fluid or hot fluid. So if we want to, let's say, calculate this one dTH, so basically it's very simply we can say that is Q dot H is equal to m dot H CPH. But something that's missed here is about this minus. It should be minus because this and delta TC is equal to Q dot cold m dot cold CPC. Okay, so something why here is minus u. We know that the values are the same, but we know that the direction of the heat transfer is not the same. For example, when the cold fluid receives the energy, the hot fluid, this is, for example, if it's a cold fluid, receives the energy, and the hot fluid gives the energy out. So that's the reason we just like put the minus here, otherwise the values are the same. So basically now if I want to say that what's the temperature difference, for example, if I say that delta TH minus delta TC, what I'm going to get, so I just like put this for example is like this for me, sorry, T is cold, and it will be equal to minus delta Q dot H 1 divided by m dot H CPH plus 1 divided by m dot C CPC. Okay, so that's what we knew from the LMTD method, and we also knew that the rate of heat transfer in the differential section is like delta Q is U dAs TH minus TC. So dTH minus TC divided by TH minus TC is equal to minus U dAs, and you just like bring this one from here. So it will be 1 m dot H CPH plus 1 divided by m dot C CPC. Okay, So integrating from the inlet to the outlet, so we will have integration. Okay, we will have T outlet minus TC outlet, T inlet of hot fluid minus inlet of cold, minus UAS 1 m dot h CPH plus 1 m dot c CPC. Okay, it just I just wanted to mention here, if you were you didn't know where those that correlation came from. So now we have that. Now that we know where this correlation came from, we can continue. But I just like mentioned that it came from LMTD. We talked about it in our previous lecture, but it's fine. It's just like a little bit of going into more detail to understand better. So I'm just going to write it down. So for parallel flow, we know it, we calculated from LMTD. So we have this one. Minus TCI is equal to, sorry, here, minus UAS 1 m dot h CPH plus 1 m dot c CPC. Okay, now we have this one. What if I just like rearrange it? We said that the heat capacity rate, so why I need always to write this one? I just like can rearrange it and write it nicer or simpler, basically. So a little bit of like a math manipulation, very simple one. I is equal to minus UAS divided by CV1 plus CCCH. So it's a bit of like a rearranging, nothing else has been done. Okay, now we also know that from the basically epsilon NTU, because now we are talking about epsilon NTU method. We don't have these outlet temperatures of hot fluid or cold fluid, so we need to find it. We also said that because there are two unknown temperatures, we can't just simply by applying the energy balance find it. But even if we can't find the exact number, we can find some kind of expression to replace them. For example, what I mean, we said that Q dot C basically is CC minus T inlet. Okay, we also said that inlet minus TH outlet, and they are equal. Okay, so Q dot C is equal to Q dot H. So even though we have this, we don't have these two, we can't find it, but we can find some kind of expression. So let me find a kind of like an expression just for outlet temperature of hot fluid. If I put everything together, so basically what am I doing is I'm saying that, let me go to the other slide. So THI minus THO HO is equal to CC TCO minus TC in. I'm not just always saying that the inlet temperature of cold water or outlet temperature of cold water is cold fluid. It's much easier to just like say CO, so, and you know it, what I mean. We want to find the expression for this one based on the rest of the temperatures. So let's say if I divide this one by CH and put it that side, what I'm having is THO is equal to THI, because I just like put it that side and brought this the other side, minus divided by CH O minus TCI. Still I can't find the exact number. Why? Because I don't have it, but I defined this outlet temperature of hot fluid based on the inlet temperature of hot fluid, inlet temperature of cold fluid, and outlet temperature of cold fluid, and based on the heat capacity rate of cold fluid and heat capacity rate of hot fluid. So this came out of equation now. Let's say replace this the outlet temperature of hot fluid here. Okay, we just replace that expression with this one and see what we are going to get. So what we are having to have is THI minus CCH TCO minus TCI is all the same as this one, minus TCO on top, and we have THI minus TCI here is equal to minus UAS, the other side won't change at all, plus CC to CH. Okay, now let's look at this one. Okay, now the only annoying things for us is this outlet temperature of cold water. And is there any way that we can get rid of that that one in a way that with some kind of very small math manipulation we can get rid of that CO? Because if we can do that, then we can have a much easier way to deal with it. Okay, so we say that how about we just like add one TC inlet and minus TC inlet, like 1 minus 1 on top is like 0, but if we add 1 and put another minus, let's see if we can get any kind of like a difference. So if we apply that one, basically I in plus V in I, or in I is better, inlet, in is the same, you can use in as well, no problem. So basically we just like added this section to it, plus 1 minus 1 or minus 1 plus 1. The rest will stay the same, but at the same time we can bring that TC outlet back to the other side as well. So I say that minus TCO minus CC divided by CH TCO minus TCI. Does make sense? Just like a very simple math basically manipulation. Bottom THI minus TCI will stay the same. But what we did here, now we have created some kind of like the same expression as here and the same expression as here, there. So that makes our life much easier. The other side will stay the same. I'm not going to write it down. Sorry. So if we apply all those like mathematical manipulation techniques, they are not like a rocket science, very simple, but it's just like adding a number, minus the same number, so it's rearrangement basically. So what I'm going to have is 1 plus, minus 1 plus cc divided by ch t o minus t I thi minus tci is equal to, the second side will stay the same, 1 plus cc divided by ch. Okay, now we have it. The only thing that we need to know now to find, because from the beginning we wanted to find the epsilon, q dot divided by q dot maximum. And for this one, we said that in this case we are solving it for when the c mean is, we just like write it c mean, let's don't make any assumption, maximum temperature difference, and q dot for cold fluid t o minus t ci. Okay, so basically this looks very familiar here. It's this one, it's exactly the same, no? So then from here we can say that Tc o minus Tci divided by Th minus Tci is equal to epsilon phi mean divided by cold. So we just like put it there, and epsilon for parallel flow. Here said that is like for parallel flow will be equal to 1 minus xp uascc 1 plus cc divided by vh 1 plus cch divided by cc. Okay, so it was not difficult. The only thing that we had to do is like we start with the assumption that we are going to talk about parallel flow. We used some kind of correlation that we talked about during the previous lecture, and from LMTD method we worked on it, and after that we got to this equation to find the epsilon or effectiveness when the heat exchanger is parallel flow. Here you can see the effectiveness of like the different steps written in order nicely, but I just explained everything during the last couple of 5 to 10 minutes, but here this slide we've summarized all of that. So now we know how to find epsilon, but finding epsilon is not our final goal. The majority of the time it's like the previous question is asking about the overall heat transfer coefficient or something like that. So we need to create some kind of relationship between the heat transfer and what we were talking about during the LMTD method and this method as well. If you remember, for LMTD method we're just saying that Q dot is like UA S, like delta TLM. But here we don't have any like mean temperature difference. We are working with NTU, so basically NTU, or number of thermal units. NTU, number of thermal unit, instead of Q, is UAS divided by C min. And basically that's it. And epsilon is a function of NTU, or number of thermal units, and C min divided by C max, that we show it here with lowercase c. Here you see that the capacity ratio. If you go to table 11.4 of your textbook, you can see that you don't have to do all those effectiveness or epsilon. You don't have to find it. Basically somebody has done it for you. The only thing that you need to do is just to go to the table and find the right correlation. The only why we did it to basically find the epsilon for parallel flow was to show you how those epsilon or correlations are coming from. But for example, for counterflow, I don't need to do all those steps. The only thing that I need to know is where the table 4 is. That when I'm dealing with the double pipe counterflow, I just come here and read or use this correlation. If I'm dealing with shell and tube, 1 shell and 2, 4, 6, 8, 10, 12 passes, I use this one, and you see that the different conditioned C max, mix, unmixed, mixed, unmixed. So there are different kind of situations. It is also, you can use those figures. For example, here you see that it's a double pipe parallel flow. Number of transfer units 1, 2, 3, 4, 5, and after that this is the heat capacity ratio, C min divided by C max. If it's 0, if it's 0.25, it's 0.2, 0.5, 0.75, and 1. And also for mixed, unmixed, different situation that we just like talked here in this table. There is another table, table 11.5, that you can see that instead of epsilon, shows the correlations for NTU. It depends to the situation, so you have all those information. The only thing that you need to do is to find the right correlation, that what you need, and after that you go to the table and you find it. Again here, if you read this box, you see that when all the inlet and outlet temperatures are specified, the size of the heat exchanger can be easily determined by using LMTD. Alternatively, it can be determined from the epsilon NTU method, but first evaluating the effectiveness of its definition, and then NTU, or number of thermal unit, from the appropriate NTU relation. So I think that's it for today, and we are going to continue to speak about epsilon NTU in our next lecture. We are just going to solve one example together, and after that we will learn a lot together. Okay, thank you so much for your attention, and enjoy the rest of your day.